So first one, the flat plate with a through thickness crack, this one, and it's subject to 100 megapascal. We have two unit systems. One is a megapascal, one is a KSI. We have tensile stress, and the fracture toughness KIC. KIC is what is KIC, guys?
Critical stress intensity.
Yeah, critical stress intensity factor, and it is a material parameter. Okay, so as long as I select this material, and this guy's KIC, which is a fracture toughness, is fixed. If we want to have a different KIC, you have got to get a new material. Determine the crack length, critical crack length for this plate, assuming the material is linear elastic. So the Ki, critical. So we have this as for this one, right? For this one, we have this is the Ki. We know that is Ki, and the Ki is written as for the through thickness crack, and the Ki is calculated as sigma and divided by pi a. So the Ki equals sigma square root of pi a, and sigma is your tensile stress you apply, and A is a crack tip you have currently you have. So this is a Ki. So this Ki is dependent upon the loading condition and also the material. So this Ki is dependent upon loading condition and material. What? However, KIC is different, and KIC is totally dependent upon your material. As I said, if you select a material, and then the KIC is almost fixed. It's just a very a little bit, and we theoretically we call it as fixed. So we want to know, given this sigma, we want to know given this sigma, and determine the critical crack length for this plate. So sigma for this problem, and sigma equals 100 megapascal. 100 megapascal. So how can we get this critical one? And critical one means that at this condition, as long as we have increased the sigma a little bit, and the crack will propagate, right? And we saw we call this one as a critical condition. Critical condition means that on KIC equals Ki. KIC here equals Ki. And KIC is fixed. As I said, it's a material parameter, and it is a fixed. But this one, we can just plug in and square root of pi a. And here we denote this A as AF, the failure, the crack length. Understand that? So this equation is a key. Then, and this guy is null, and sigma is null, and pi is null, and you can calculate this AF. So keep in mind, this AF for this through thickness hole, it is half of the crack. If I ask you total crack, that means 2A, okay? And be very careful. And this is kind of tricky. For the edge crack is the total length of the crack. But theoretically, it's also still the half, right? Do you agree? So we just denote as half. And so this is the first problem. And second problem, and compute the critical energy release rate GC. Compute the critical energy release the GC of this material. And now this time Young's modulus is given. And for this one, we have the equation G, right? And G equals on Ki square and by Young's modulus. Right? Okay. For this GC here, and GC equals KIC and square and divided by Young's modulus. Do you still remember this equation, right? Right? this equation? Questions? Okay, this is our second problem. Second problem, you can get the second problem, answer for the second problem. So this problem, the 1.4 is a very good one. So do you still remember what is the dimensionless analysis, guys? Huh? What is the dimensionless analysis, Dylan?
You just kind of like get everything in terms of three variables that have the characteristic dimensions.
Yeah, okay. So first, we need to identify which is the fundamental. This is the unit. For this one, what is the fundamental unit, guys?
Time.
Yeah, for this case, time is the fundamental unit. So time. Second. Huh? Okay.
What?
Yeah, you said something, right?
Like the height.
Yeah, height. Yeah, height. What's the height is length, right? And this is height is the length. Anything else? The mass. Mass is mass the is a basic unit. Okay, then we have this mass. So then what should we do, guys? We dimension this guy. How can we dimension this? So let me tell you guys, what is the G, guys? What is the unit of the G? The G for the G, we have the length divided by second square, right? Right?
Yes.
Okay. And then for each of these variables, we need to dimension list them. And how can we dimension list them? And for the t, we dimension list use this second, and also this L, we use this is a 0, power 0, exponent 0. Right? And for this G, this is L, and which is second. This is a second square. We can dimensionless it. And for this M, we do not have anything to do with this M here. M here has nothing to do with the T, has nothing to do with H, have nothing to do with G. You guys agree? As a result, for this equation, and the T has nothing to do with M. Is this consistent with what we have learned? Sparta, right? Somewhat. Okay. Somewhat. You understand, Suyo? No? Okay.
So the mass has nothing to do with the gravity, but the total function of the time flight, the flight time, the mass does have something to do.
No.
No.
Yeah. If you drop this is the free body, this is the object. And no matter how high it is, no matter what kind of mass it is. And so the T has nothing to do with this M. T only is dependent upon H and G. Understand? So I want you guys to take a look at this one. I give you some room to explore by yourself. And tell me why, based on these the units, I can determine immediately the T has nothing to do with M. If you can show that what I said is wrong, okay, with the hard evidence, then we will publish a Nobel Prize winning this the paper. Okay, we just validated that. We just disapprove what Galileo has said is totally wrong. I'm kidding. Okay, guys. So this is the time for the free body to reach the land from the original height. Has nothing to do with the mass. Has nothing to do with displaced mass. If you do the dimensional analysis, you will know this one. So you can see on how powerful dimensionless analysis is. So, is this helpful for you guys for the finishing your homework? Finishing homework will be due what time? I forgot.
Friday,
Friday what time?
before the class starts.
Yeah, before the class starts. Can I finish? Do you need more time? No, right? Yeah, before the class is okay. I think it's fine. You can just finish these two almost done. And for the third one, just look at lecture notes and get more have deeper understanding of dimensional analysis, dimensionless analysis, and then just explain. Alright? So you need to prove that and how the M, why the M has nothing to do with the time. So without further ado, I'm going to continue our talk. Last time we talked about this is the load control and this is the displacement control. And can somebody just tell us what is the load control and what is displacement control? Can somebody tell me, Dylan? Want to say?
Load control has like a constant load or force being pulled on it, and then constant or the other one
Displacement control.
has just the fixed displacement, but the load varies.
Yes, load varies when this is a crack length changes. Okay, so this is a very good, some good element. So let me repeat. Load control means that load control means that I have a cracked body. Is a crack will grow, right? So as the crack grows, the load I apply does not change. The load, the weight does not change. I mean, the externally applied load does not change. So this external load does not change, but I can establish the relationship between this is a load, between the crack tip and the displacement. Right? So this is a load control. And however, for this displacement control, on the contrary, displacement control, the displacement of this displacement does not change, but the crack is growing. As long as the crack grows, and we know that this body, this is the specimen becomes softer. Right, guys? Becomes softer. That means the applied load required to achieve this desired displacement becomes less and less. You guys agree? Okay, so this is load control, and this is and displacement control. So we usually in our this is you have taken the mechanics lab, right? Have you taken a mechanics lab? And you applied we have a specimen, a steel cast iron and also steel cast iron, another one is aluminum alloy. You have done the tensile test, right? You have done the tensile test, right?
Yes.
The tensile test, for the tensile test, is this a displacement control or load control? It is not load control and not this displacement control. Okay, but that is different one. I just want to tell you. For this is D control and load control, and this is for cracked body. For cracked body. For cracked body, we want to see on how either the displacement is dependent upon crack length and to maintain the same load, or on how this load is dependent upon this crack length to maintain the same amount of displacement. So you should know that. Here, so energy release rate, and we talk about this energy release rate. And for D control and L control, we have two equations. And so these two equations, and you should know that. Okay? You should know these two equations. Let me ask you guys, what is the delta? Delta is a displacement. Delta here is a displacement. Right? So this D control means the displacement does not change. So here this delta is a displacement, and here is a subscript delta means the displacement control. It does not mean anything else. It only means that this is a displacement control. So here you can see for displacement control, my displacement remains the constant, but what is changed? P. Right? If the crack grows, the P will be changing also. Why? Because if we want to maintain the desired amount of displacement, if the crack grows, that means the cracked body becomes a softener, and you need to the needed load will be decreasing also. So that's the reason we have a negative sign here. Okay, is it sharing? No. Okay. For load control, on the contrary, for load control, the P, the applied load, it remains the constant, remains constant. This case does not change. So what is changing? For the load control, what is changing? The changing is crack length and the corresponding displacement. Right? If we, as I said, if the crack grows, so this specimen becomes softer. If I still have the same amount of load, definitely this case displacement will become bigger. Right? Right, guys? Are you following me? Or totally confused? Obi?
How do they change the crack length, like in the actual experiment?
Crack length, when you do this one, the crack will grow.
Or it will just automatically grow?
Yeah, I will not say automatically, add some condition. Yeah, you can say automatically, under some condition, if you have this load, you can see it grows. So to do this load control, you need to follow some ASTM the protocol. You guys know what is the ASTM protocols are? Okay, so whenever you do this, for tensile testing, compressive testing for different materials, and also D control, load control, and for any other the testing, you must follow the standardized protocol. We call ASTM, American Society of Testing and Materials. What? So compliance. What is the compliance? We know the stiffness, right? We know the stiffness, and stiffness is the ratio between the load with respect to deflection, right? But compliance is the reciprocal of the stiffness. Right down, guys. Compliance is the reciprocal of stiffness. Stiffness equals usually is the stiffness and the stiffness stiffness equals load multiplied by the corresponding deflection. The compliance is just this guy's reciprocal and equals delta divided by P. So C equals this one, so we can get G here. So this is G, this is G equals P squared and 2B divided by DC and DA. And we know for both cases, the compliance is changing. Why the compliance is changing? Because the crack length is changing. Crack length is changing. That means your material becomes softer and softer. So that's the reason we have this G can be written as P squared divided by 2B and DC dA. C is the compliance and A is the crack length. What is the capital B, guys? Yeah, thickness. Thickness of the plate. Capital B is the thickness of plate. And for this equation works for both load control and D control. Any questions so far? Any questions, guys? No question? No question. Let's look at the for load control. Okay, load control. We know that definition C equals delta divided by P. C compliance C. C and is a compliance equals delta divided by P. So delta equals for load control and delta equals C multiplied by P. And then we know that D delta dA equals DC dAP. Why? Because the P is a load control and P is a constant. I just take this constant out. I only have the derivative of C with respect to A. Right? So on the contrary, for D control, the P is written as delta divided by C, right? D divided by C. And so for original equation, we need to have dP dA. So this one equals negative delta dC dA. So here, for D control, you can see D control, and we need to have a P here. And P here, you can see P is the function of the crack tape, of crack length. So dP dA equals this. So there are the observations here. If no crack extension, right? For load control, if no crack, there's no crack there. For load control, du increases. What is U? And U is a straight energy. U is increasing. U is increasing. For displacement control, du equals 0. For displacement control, if no crack, this guy equals 0. So if crack extends, if the crack grows, so du straight energy is increased for load control, and for the straight energy is decreasing for the displacement control. And we have these two observations. Why? And you can see the graphical representation last time I showed you, and you will know that. So total potential energy equals U minus F. F is the work has done by the applied force. Keep this in mind. For load control means that we have the external applied force. As a result, we have This is the work has done by the externally applied force, but for displacement control, and the F equals 0 because the displacement does not change. Questions? Comments? Then let's look at the example, guys. Okay, this is we have this double cantilever beam, the DCB specimen, and the thickness thickness is a B. So here is H. So this is the delta, the displacement between these two the tape, these two tape cracks. This is crack tape. Between these two tapes, and they are where is the delta. The crack length equals A. And for this one, determine the energy release rate for double the cantilever beam DCB specimen. Look at this equation. So, and how to solve this problem? And we use what we have learned. And what we use what we have learned here. So this is the we calculate the G here. So how to calculate the G? We use this equation, okay? So this is how to calculate the G here. And first, the two delta, we can get this two half delta. So this one, the half delta can be written as 3P applied load. You have a load P here. This is applied load A cubic EI. So how can we calculate this one? There is an equation. Here is an equation. Okay, I will not show you how to derive this one. But we know that for the DCB, and we know the displacement for the tape from the original point can be calculated using this equation. P is the load, A is the crack length, and EI. And EI equals this. And what is this, guys? What is I? What is I?
Moment of inertia.
Yeah, I is the moment of inertia. Keep in mind, this is a plate. If we see the cross-sectional area, it is rectangular. Okay, rectangular. This guys, the area moment of inertia equals 12. The base multiplied by h cubic. You still remember that one, guys? So base, if I just cross section, if I see from this side, the base is the thickness, right? The height is h here. So this one, this equation is well established equation for these kind of things. But we just use this equation, just take this equation from the theory. And now what we want to know is the deflection delta. The delta is the same as here. Okay, so this is delta. Generally speaking, so this is the displacement. So you can see the C is a compliance, and the delta divided by P equals this. Delta divided by P equals this one. Then I take the derivative of the load. Load does not change. The load does not change. It is load control. And then I have dC dA. And dC is derivative of dA. Right? So here is the 3, this is 3. Just come down, cancel this out, right? I have 2a squared and EI. So dC dA. And then this using this equation, and for this is this one load control, you can see load control, okay? P does not change, 2b d delta dA with respect to P. So we use this equation, and then we can get, and for this case, G equals this. Okay.
How come it's P squared down there, whereas the load controlled is just P?
You are right. Just one second. Let's see. Would be. Yeah, you are right. Okay, so this is the P here. Okay, the P. I'm sorry. Sometimes I have some.
Cause that's the one that we said works for both of them, is the P squared over T two B. Like the,
Which one?
working for both L controlled and D controlled, the P squared over two B.
Oh, here. Oh, here.
So is that equal to the P over two B? I guess when would you use one over the other? Oh, it's because we have DC over DA, not D
Yeah.
delta over DA.
In the C.
Okay,
Yeah, that's a P. Here is a P power one, right?
right,
This is a power one, but here is a power two.
okay,
Because we have C here.
okay. I
And
see.
C is a function of P. That's good question. We can just clarify this equation.
So could you have done it with you just finding D delta over DA and then using the L controlled equation? Or,
Yeah, you can do that. Yeah, the same thing. Bobby, you can just try, okay? Using this equation instead of this one. The same thing. Yeah, good. So this is the square. This is the square. Any questions? Any questions, guys? No question? We move on to next one. Next one is instability and R curve. Instability, you can, and as the name suggests, we want to see under what condition, so this crack is going to grow. And after it grow, will it grow continuously, or after it grows a little bit, then it stops? So this is called instability. And R curve, R is called resistance. R is called resistance. And you can look at this curve, this is the diagram. So here, Tc is the critical energy release rate. Tc is a critical energy release rate. It is the material parameter. And T is the actual energy release rate that is dependent upon your loading condition and your crack length. And we want to compare this is G and R. If R is resistance, if G is greater than R, we have the crack grows. If G is less than R, the crack does not change. And let's talk about this. G is energy release rate, and it equals 2 times fracture energy. This is 2 times fracture energy. If this equation holds, the crack will grow. Okay, we introduce a new concept R. R is resistance, write down as R is resistance of the material. Let the resistance equals 2WF, that means R equals 2WF, and R is the material resistance to crack extension. So here is one example for this through thickness crack. And from through thickness crack, guys, you can see G equals pi sigma square A divided by Young's modulus. So this is the energy release rate for the through thickness crack, central crack, and sigma is the applied load, and A is your current half of the total crack length. Right? So we can calculate the T here. You can see, guys. You can see T is a TR, and we have a TC. For brittle material, R is constant. Write down, guys. For brittle material, the resistance of material is constant, and the crack growth will be unstable. And what does that mean? It means that if the crack grows, and then theoretically, you will have no control, and it will crack propagates until the whole specimen breaks. Why? Because the R is a constant. I'm going to show you guys. And for ductile material, and crack growth, if G is greater than R, energy release rate is greater than resistance, crack growth, if G is less than R, and the crack stops. So for ductile material, we can achieve some stable growth. This is a critical condition. Let me show you guys. So here you can see, okay. So for this is R, and suppose at this point, you can see at this point the TC equals R, TC equals T. It will grow, alright? It will grow, guys. Can you see? Can you see? It will grow. If it grow, the T will always be greater than the TC, than the resistance. As a result, so this one will not be stable. That means as long as this exceeds zero, so this is the crack will continue until the whole body breaks. Why? Because the resistance R is constant, and you just break the stability. I will break the stability, and you cannot stop. So keep in mind, here R is TC, right? And we just use the letter R to denote TC. Dylan.
So is that a graph for a brittle material then?
Yeah, this is for brittle material. For brittle material, the R is a constant. It does not change with respect to the crack length. But on the contrary, for this curve, so this curve, the R is rising. R is not constant. You can see my R is continuously rising without the flattening. You can see without this leveling out. And for here, for this one, as long as I have a T here, okay, as long as for this curve, so this curve is tangent to this R curve, and then you can get a new crack length. But I will get a new crack length, so my new T, will go here, and my new T go here. Then what will happen? So at this instant, so this new T is less than the new R. As a result, this guy will stop. One more time, guys. At this instant, suppose for this is sigma 4 for this one, and this is the line is tangential to this R curve. This R curve, it means that it will have crack propagation, right? If you have a crack propagation, it goes here, and then you can see my R is continuously growing. But at this point, this new T is less than the new R. That's the reason, so this crack will stop here until you have new. This is the higher the load. For this is the stable growth. For both stable growth and this is unstable growth, the prerequisite condition is that T is this condition is met. T equals R. That means T equals GC. You should keep in mind here, okay? The resistance and V equals the GC. I just want to tell you guys for the TC and for convenience, because sometimes the TC is increasing. Sometimes the TC increasing, we use R here. So for stable growth, T equals R, but the change of T is less than the change of resistance. If this condition is met, and this is stable growth. Stable growth means that the crack grows a little bit and then stop. And however, for unstable growth, so first, this is a prerequisite condition must be met also, but at this time, if the change of energy release rate is greater than the change of resistance, and then that means, this is a crack propagation cannot stop. Easy. Okay? Yeah. Okay. Did what I said make sense to you? So we are comparing, we just continuously compare, this is the energy release G, energy release rate G, and the R resistance. So, for this is for the R shape, okay, so R, the shape of R. So R is a flat, if the material is brittle, it means surface energy is the main resistance. The surface energy is the main resistance. That means, so surface energy is dominant. And plastic deformation and any other, this is a material behavior does not change is the surface energy. So this is, we know, if R the flat material is brittle, the R is a flat. However, if R is rising, okay? If the material is ductile and the surface energy is a smaller part of resistance, that means large part is a plastic work. If this is the case, the R is rising. The R is rising. That means as this is the crack growth, the plastic deformation occurs in front of the crack tip. As a result, for further crack growth, you must dissipate more energy and to just overcome the existing plastic deformation area. So in this case, R is growing. However, for brittle material, okay, for brittle material, if surface energy and local plastic dissipation, we have surface energy and also local plastic dissipation. So this R is going down, the R is falling. If this one is the case, that is a disaster. You know cleavage, right? Cleavage is, that means if the crack grows, if the crack propagates occurs, you cannot stop. This even much worse than this is when this R is flat. It becomes decreasing. It is decreasing. Questions so far? No question. We talk about this is the plane stress and plane strain, and you guys know what is a plane stress and plane strain, right? And plane stress means that the plate is a thin plate. And plate is thin. Plane strain means that the plate is thick. So being plane stress or plane strain can also affect the R curve. And how to get the R curve? How to get the materials R curve? So we need to come back to the ASTM protocol, relevant protocol, and to do the experiments and to get this is R resistance curve. You understand? You can see we cannot do any research without ASTM. This is the protocols, and they are commonly accepted protocols. For D control, let's see the D control. For displacement control, you can see for displacement control, the driving force goes down with crack growth. You can see these dotted curves, they are displacement control, delta. However, for this load control, you can see for load control, and the driving force, this is going up with crack length. So this is based on this equation, G equals sigma square A E, and when A goes up, A G goes down. These are for any questions?